Okay, so we are talking about point dipole in a electric field, and we saw that the dipole strength is inversely proportional to the square of the distance. Okay, so this is what we are talking about. So we are talking about a dipole. So we have plus q here, minus q here, separated by a distance d, and we are seeing how the potential distribution because of this dipole is looking like. Okay, so we saw that the potential distribution phi total at some distance r will be b cos theta over r square plus phi rest r. Okay. So this is the expression for the potential at any point, and this contribution is coming from the dipole. Okay, here B is equal to P, which is the dipole strength, divided by 4 pi epsilon. Okay, so P is the dipole moment, and this may be because of the external sources. Okay. Okay. So this is what we saw. We saw that if we have a dipole, its effect at any point r in terms of the potential distribution is going to vary as the inverse of the square of the radial distance. Okay. So with that let us move on and talk about a dielectric sphere in a dielectric liquid. Okay. So if you have an electric field present in the dielectric liquid, the presence of the dielectric sphere is going to modify the electric field, and we would see how the dielectric moment the dipole moment is going to vary in space. Okay. So this is the situation we will be talking about. So here we have a positively charged plate and negatively charged plate. So we establish an electric field. Okay, and let us say the dielectric constant of the fluid is epsilon 1. Okay. So the dielectric fluid here is being penetrated by the electric field epsilon 0. So we can write the potential variation phi 0 as a function of r, theta and psi, which is the azimuthal coordinate, equal to minus E0 into x r theta psi. So in this case the electric field is varying only along x direction. So the theta and xi there is no dependence. Okay. And so this is going to be minus E0 into x. X is nothing but r cos theta. In this coordinate system here, x is r cos theta, and here we have a negative sign. This indicates that as x increases the potential is going to reduce. Okay. So that is denoted by the negative sign there, and if you have now we have a dielectric sphere. If you look at the right side figure here, okay, so we have a dielectric sphere which dielectric constant epsilon 2 is introduced into the liquid. Okay. So we have an electric field which is maintained because of two oppositely charged plates, and so we know the electric field okay. We know the potential how it is varies along x, okay. Now we introduce a dielectric sphere into the medium, okay, and whose dielectric constant is epsilon 2. So we introduce a sphere and the dielectric constant is epsilon 2, as you can see in this figure here. And when we introduce this sphere into the uniform electric field, the electric field itself gets perturbed, okay. So because of the presence of the electric field, this dielectric sphere is going to be polarized, and the polarization of the dielectric sphere is going to perturb the electric field, okay. So and that is what we see here, the uniform nature of the electric field is perturbed, and the whole electric field gets modified as you see it here on the right side, okay. So we can say that because of the modification of the electric field, the potential distribution also changes. So let us say phi is r theta psi is phi 1 r theta. So here we are talking about a sphere in an uniform electric field, so there is no azimuthal dependence, okay, psi there is no variation along psi. So the two coordinates which are important is r and theta, okay. So let us call the potential inside the liquid is phi 1 r theta when r is greater than a, okay, and the potential is phi 2 r theta when r is less than a, okay. Now to obtain the distribution of this potential, we have to solve the Laplace equation. So the Laplace equation, which is nothing but del square phi r, is going to be 0, and so here as you said before, there is no dependence on azimuthal coordinate, no dependence on psi, okay. So we can write a general solution, and the general solution for this Laplace equation in this case considers Legendral polynomial in the solution, okay. So the phi r theta is going to be summation L equal to 0 to infinity a L r to the power L plus B L r to the power minus L plus 1 into P L into cos theta. So this is the general solution of the Laplace equation for this case, and so L is, so AL and BL are coefficients of the Legendre polynomial of the Legendre polynomial. PL is the Legendre polynomial, and L varies between 0 to infinity, okay. Now these coefficients of Legendre polynomial can be determined using the boundary conditions, okay. So let us look at what are the boundary conditions that we use to evaluate the solution. So the boundary conditions The first boundary condition is that the potential phi 1 at r equal to a theta will be equal to phi 2 at r equal to a and theta. So there will be no discontinuity in the potential. Okay, so here we say that phi 1 is outside the sphere and phi 2 is inside the sphere, but here we say that the boundary condition, the phi 1 at r equal to a should be equal to phi 2 at r equal to a. So there is no jump in the potential. The second condition is that epsilon 1 into del over del r into phi 1 del over del r of phi 1 a theta is going to be epsilon 2 del over del r of phi 2 a theta. Okay. So this is saying that the normal component of the electric displacement is continuous. Okay. Electric displacement we have seen earlier can be written as epsilon into electric field. So this gives us the normal component of the electric field. So we say that the normal component of the electric displacement is continuous. The third boundary condition is that the potential phi 1 r theta when r tends to infinity, and this when r tends to infinity, if you see here at r tends to infinity the electric field is unperturbed. Okay. So the modification of the electric field or modification of the potential distribution is around the sphere. As we move away from the sphere, far away from the sphere, the electric field is still unperturbed, the potential distribution is still unperturbed. Okay. So we can say that at r tends to infinity the potential distribution is same as the unperturbed potential, so r cos theta, and this is the value when before we introduce the sphere into the electric field, uniform electric field. And the last boundary condition is that phi 2 0 theta is finite. Okay. That means the potential at r equal to 0 has a finite value. So with these four boundary conditions we can use to evaluate the unknowns in this solution expression for phi r theta. So if we do that, we can write the expression for phi. So phi r, okay, is going to be minus epsilon 0 into r cos theta plus epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into aq E0 cos theta over r square, okay, which is equal to, so this is nothing but the unperturbed potential when you do not have the sphere in the uniform electric field. So phi 0 r, and this potential is because of the dipole. Okay, since we introduce a dielectric sphere in which the dipoles get developed, so this potential comes from the dipole that gets introduced inside the sphere. So the dipole potential, okay, and this is valid for r equal to r greater than a. So this is r greater than a. Okay. Now we have another solution when r is less than a. Okay. So that would be minus 3 epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into E0 r cos theta, which will be equal to minus 3 epsilon 1 epsilon 2 plus 2 epsilon 1 into phi 0 r, r less than a. Okay. So this is for r less than a. Okay. So what we see here is that the potential phi 2, so this is nothing but phi 2, right, this phi 2, this is inside the sphere, and this is nothing but phi 1, okay, phi 1, right. So what we see here is that the potential distribution inside the sphere is directly proportional to the unperturbed potential, okay, phi 0 r. So phi 2 r is going to be proportional to phi 0 r, which is the unperturbed potential, and the potential distribution outside the sphere, okay, phi 2 r is going to be related to the dipole potential. Okay. So the two things we observe from here. So we observe that the potential phi 2 inside the sphere is proportional to unperturbed potential okay. So this is what we see here, right. So phi 2 r is directly proportional to phi 0 r, and the second observation is that the potential inside in the liquid outside the sphere is related to the dipole potential. Okay. So the potential phi 1, which is outside the sphere, depends on the dipole potential. Now if you compare this term here, which we say that it is because of the dipole that gets induced inside the sphere with the potential because of the point dipole, okay, and that is something we saw here. If you compare that with this expression, which is the potential distribution because of a dipole, okay, then we can express what is the dipole moment for the sphere case. Okay. So the phi dipole is epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into a cube E0 cos theta over r square. So that is the solution what we saw here. Okay. Now if you compare that with the dipole potential, which is we derived earlier, is B cos theta over r square, where B is 4 pi epsilon into P. So, from there we can obtain for this case, for the sphere case, what is the dipole potential, okay, dipole moment, sorry. So, we can say the dipole induced dipole moment P is going to be 4 pi epsilon, okay, into epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into a cube into electric field, okay. So, that is going to be the expression for the dipole moment P, right, and this parameter here epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 is called Clausius-Mossetti factor. Clausius-Mossetti factor. So, you can write the Clausius-Mossetti factor K epsilon 1 epsilon 2 is epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1, okay. Now, what we see here is that the direction of the induced dipole moment is dependent on the, with respect to the direction of the electric field, is dependent on the Clausius-Mossetti factor, okay. So, if the sphere is more dielectric than the liquid, so epsilon 2 is greater than epsilon 1, then the dipole moment and the electric field are going to be parallel, okay. So, what we observe here is if the sphere is more dielectric than fluid, so that is epsilon 2 is greater than epsilon 1, then the induced dipole moment P and the unperturbed electric field which is E0 are parallel. Okay. So, they are going to be parallel, and if you see that the medium is more dielectric than the sphere, then the direction of the induced dipole moment and electric field are going to be antiparallel. So, if the fluid is more dielectric than sphere, that means epsilon 1 is greater than epsilon 2. So, the dipole moment and the electric field are antiparallel, and if the dielectric constant of the fluid and the sphere are equal, then the dipole moment is going to vanish, okay. So, the dipole moment is 0. Okay. So, with that discussion on the dipole moment, let us move on and talk about what is the dielectric force that can act on this dielectric sphere when it is present in an electric field. Okay. We have discussed how the induced dipole moment is going to look like when it is placed in an uniform electric field. So, the expression for the dipole moment is relatively simple, but when this is placed in a non-uniform electric field, okay, in that case we would only realize that there is a dielectric force that exists. So, in case of a non-uniform electric field, the calculation of the dipole moment is more involved, because in that case we will not only have dipole moment, but we would also have multiple moment, meaning we would not only have only a cluster of positive and negative charges, which would give you a single positive cluster, single negative cluster, that will give you a dipole, but we would have multiple moments. Okay. But if we assume that the radius of the sphere is very small as compared to the length scale of the field, still we can assume that we would have only dipole moment existing. Okay. So, let us look at the dep force or the dielectrophoretic force, dp force in a non-uniform electric field. So, dp force on a sphere. In a non-uniform electric field. So, in this case the calculation of dp force or the induced moment is complicated. So, this is because we have dipole moment. Present. Okay. But if we say that the radius of the sphere is less than the length scale of the field L, then we can expand the electric field around the center of the sphere. Okay. So, in that case we can expand the electric field using Taylor series around the center of the sphere. Okay. So, if we do that, we would say epsilon 0 into r is going to be epsilon 0 r 0. So, that is the center of the sphere, plus r minus r 0 into the gradient of the electric field. Okay. So, which is nothing but E 0 r 0 plus a term which is of the order of A over L, and since A over L is negligible, this term can be dropped off. Okay. So, we can generalize the dipole moment, okay, as P we can write it as A cube into 4 pi epsilon 1 into the Clausius mosity factor epsilon 1 epsilon 2 into P0 R0. Okay. Okay, so what we see here, this is what we derived, right. So this is the electric field. So instead of writing the general electric field, we are writing this electric field around the center of the sphere, and this is when we are talking about a non-uniform electric field. Okay. So now we can determine the dielectrophoretic force. Or the dp force, and we had looked at the formula to do that. So F dp is going to be the dipole moment to the gradient of the electric field, right. So this is going to be equal to P R0 into gradient of the electric field R0. Okay, so this is the vector. So that is going to be 4 pi epsilon 1 into the Clausius mosity factor into a cube. So we have one electric field coming from there, and there is one more here. So that becomes, we can write it as E0 R0 dot gradient of E0 R0. Okay. So this would become 4 pi epsilon 1. Now this we can take this expression for the electric field, we can take it inside the gradient, and so that will become E0 R0 square. Now when it comes out of the gradient, it becomes twice of the electric field. So here we can observe 2 in there. So this becomes 2 pi epsilon 1 into k epsilon 1 epsilon 2 into a cube into gradient of the square of the electric field. Okay. So this is going to be the expression for the dielectrophoretic force. Okay. So that dielectrophoretic force would depend on the Clausius mosity factor, the dielectric constant of the fluid, the size of the sphere, and the gradient of the square of the electric field. Okay. So what we learn from here is that the dielectrophoretic force is independent of the sign of the electric field. Okay. And it is dependent on the square of the gradient of the square of the electric field. It is directly proportional to the third power of the size of an object, and it is the sign of the dielectrophoretic force is dependent on the sign of the Clausius mosity factor, and it is going to be proportional to the dielectric constant of the fluid in which the object is present. Okay. So what we observe from here is that the dp force is proportional to third power of the size of the sphere. So, although here we are talking about a sphere, in general the dp force is going to be proportional to the third power of the size of an object. So, this can be used in microfluidics to sort objects of different sizes, okay, where for a smaller object the dielectrophoretic force will be less as compared to that for a larger object, okay. So, this can be used in microfluidics for sorting of objects like cells, okay. For example, if we let us consider a channel and we are able to establish an electric field in this direction, okay, and here we have a mixture of small and large objects, okay, and assuming that they have the same dielectric properties, then because of the electric field the larger objects will be subjected to larger dielectrophoretic force. So, they will move towards the wall, okay, irrespective of their initial position, they will be moving towards this wall, and the smaller object will tend to remain in their original position, okay. So, they can be separated, okay. So, where you can take out smaller particles and separate it from larger particles, okay. And we also observe here that the dp force is governed by the direction of the gradient of square of the electric field, okay. So, even though the dielectric force will not depend on the sign of the electric field, it will depend on the gradient of the square of the electric field, okay. And the other important observation is that, so here we say that dp force does not depend on the sign of the electric field, okay. So, that is, so the other important observation is going to be that the sign of dp dielectrophoretic force is given by the sign of the Clausius-Mosetti factor, okay. So, you can see from this equation here the direction of the dielectrophoretic force is very much dependent on the sign of the Clausius-Mosetti factor, and if the sphere is more dielectric than the liquid, the dielectrophoretic force is positive, okay. And this is a requirement when you are talking about, let us say, trapping of particles, okay. In microfluidics, in some applications we are required to pull particles from the bulk of the liquid towards an electrode. So, in doing so you would require the dielectrophoretic force to be positive, so they can come towards a specific point or towards the electrode. So in order for the trapping to occur, the dielectric constant of the objects or the cells or the particles has to be higher than the dielectric constant of the liquid. Okay. Okay, so for particle trapping, using dP, the dielectric constant of the sphere has to be greater than the dielectric constant of the liquid. Okay. So with that, let us move on and talk about trapping of particles in microfluidics. Okay. So this is the case we have here. We are talking about a rectangular channel. So the bottom wall is at z equal to 0 and the top wall is at z equal to h. So the flow is in the x direction, the positive x direction. So what we have here, as I told, for the dielectrophoretic action to come into play, there has to be a non-uniform electric field. Okay. So if you look at here, we have an asymmetric electrode configuration. On the bottom surface of the channel we have a hemispherical electrode. So this is a hemispherical electrode, and at z equal to h we have a flat electrode. So this top electrode is flat. So we create an electric field having phi equal to 0 at the top electrode and phi equal to some positive voltage at the bottom hemispherical electrode. So we create an electric field, however this electric field gradient is positive in this direction. Okay. So the lines are more concentrated close to the hemispherical electrode. So in this direction we maintain a positive electric field. Okay. So when the particles are flowing, okay, there are two forces that will come into picture when you are talking about trapping. One is the dielectrophoretic force, which will come into picture if you are trapping towards the electrode, it has to be positive. Okay. And for that to happen, the dielectric constant of the sphere has to be, or the particle has to be more than that of the liquid. So that is the first force. The second force that comes into play is the drag force, which is trying to carry the particle along with the flow. Okay. So we are talking about forces acting on a particle. One is the dielectrophoretic force F dP, and the other one is the drag force. So you would calculate the dP force and drag force individually, and for the balance for the trapping to occur, the dielectrophoretic force has to be greater than the drag force. So this has, the dielectrophoretic force has to be greater than the drag force for trapping to occur. Okay. Right. Now we, for the rectangular microchannel, so here we say that the height is h and the height h is less than w, which is the width. So here we are talking about, so this is H, okay, and this is W. We say that H is less than W. So it is almost a parallel plate flow situation. So this is parallel plate case, and in that case we know the velocity profile looks like, so u into z, z is here, so this direction is z. So the velocity profile uz is given by delta p divided by 2 eta L into h minus z into z. So this is how the velocity of the fluid containing the particles is going to vary, right. So we can also write this in another form. We can write uz is going to be 6 into 1 minus z by h into z by h into u0. u0 is the average velocity, okay. So u0 is the average velocity, which is q over wh. So we can find an expression for the drag force. So drag force, F drag is going to be 6 pi eta into radius of the particle into ur, okay. So we do not know where the particle is, so let us say our particle is present at some location r where the velocity is ur, okay. So now we have to first find a potential distribution between the two electrodes. Since we have one spherical electrode, one flat electrode, to find the potential distribution we will be using the method of mirror, okay. So in what we will be doing is we will be considering another spherical electrode as a mirror image, okay, on the opposite side of the top electrode, and considering that we will be finding out the potential distribution, and knowing the potential distribution we will try to find an expression for the dielectric force. We will compare the dielectric force with the drag force. For the trapping, dielectrophoretic force has to be greater than the drag force. So we try to find out there has to be a limit on the maximum velocity of the particle above which trapping may not be possible. So we try to find the limiting velocity of the fluid, okay. So we will continue this. With that let us stop here.